Mm, Welcome to this online tutorial on compact subsets of a real line. So we are going to first define what it means for a set to be bounded. Definition. Let A be a subset of R. So we shall say that A is bounded. A is bounded if there exists some positive real number which I'm calling K, such that the absolute of x is less than K for all x in K. So a set is bounded if there exists some positive real number K, such that all elements in the set are less than that K. So that's what it means for a set to be bounded. You can take some example. The interval examples, interval 0, 1 is bounded. That interval is bounded. This is bounded above by 1, below by 0. So each number which is between this interval, for example, you can take 0.5. 0.5 is less than 1. It's less than 1. It's less than 1. So this interval here is bounded. You can also take another one. This one also is bounded. So we are going to evoke an important proposition which is going to help us understand the compact subsets of a real line. So what is that proposition? Every compact subset of R is closed and bounded. Theorem? Every compact subset of R is closed and bounded. That is a very important theorem. We are saying that every compact subset of R is closed and bounded. So if I'm saying that you are compact, then you have to be closed and bounded. For example, this interval 0, 1, this is closed and bounded. So since it is closed and bounded, it is compact. It is compact. Observe that this interval here is not closed. That is an open interval, hence it's not compact. We are saying that this is compact, closed and bounded. This is not compact. Now you can easily relate how we are trying to develop the compact subsets of R. Actually, this is a compact subset of R. This is not a compact subset of R. Since it is open, since it's an open interval, however, it's bounded. So how can we prove that theorem? How can we prove this? We are going to let A be a subset of R. Let A be a subset of R such that A is closed. Every compact subset of R is closed and bounded. Is closed and bounded. So for that case, what we are going to, so we are letting A to be a subset of R. We want to show that every compact subset of R is closed and bounded. So suppose that A is a subset of R. Suppose that A is compact. Suppose that A is compact. So we are supposed to show that A is closed and bounded. Closed and bounded. So what do we know? Let me hope that you still remember what a Hausdorff space is, what a T2 space is. So actually R is a T2 space. R with the usual topology. The usual topology. R with the usual topology, just a collection of open intervals. Is T2. For a T2 space, if you remember in the previous videos, for a T2 space, if you can, if for any 2 points, x, y in R, these being distinct, the question is, can we find 2 open sets which can enclose both of these points? Can we find an open set which can enclose x and an open set which can enclose y? And when these 2 sets are disjoint, this is U1, U2. Can we find such open set such that x is in one open set, y is in another open set, and these 2 open sets are disjoint? Actually, in R we can construct such open set. For example, we know that 1 and 2 are real numbers. 1 and 2 are real numbers. Since they are real numbers, they are also different. So we can find this open interval from what? 0.1 to 1.1. This is an open interval containing 1. Then you can also find this open interval 1.9 to 2.1. So this is an open set containing 1. This is an open set containing 2. So these 2 sets are disjoint. So that means R is a T2 space. R is a T2 space. It's a Hausdorff space. So we are saying that A is compact. A is compact since R is T2, since R is a Hausdorff space, in the previous sessions we proved that every compact subspace, what was that? I always forget that thing. It was every compact subspace of a Hausdorff space is closed. Every compact subspace of a Hausdorff space is closed. So A is a compact subspace of a T2 space. So we can now conclude that A is actually closed. Yes, every compact subspace of a Hausdorff space is closed. We prove that. So A is closed by the previous results. What next? We are left with proving that A is actually bounded. So what do we know? We know that R is. So let us first construct an arbitrarily open curve of this R. So we want to show that A is bounded. Let this, I think we looked at this set and we said that this is an arbitrary open cover of R. Let this be an open an open cover of R. Let that be an open cover of R. So since A is contained in R, since A is a subset of R, comma, then since A is in R, comma, then this set here is an open cover. Is an open cover of what? Is an open cover of A. Is an open cover of A. Since A is compact, comma, then A has a finite subcover. Since A is compact, A has a finite subcover from that set. So A has a finite subcover from that set. So how does that finite subcover look like? A has a finite subcover from that set. So let this finite subcover, let this be gamma negative n1 up to negative nk. That is the finite subcover of A. That is the finite subcover of A. So if we let M be the maximum of n1, n2 up to nk. Now if M is the maximum of those natural numbers, we can take an example. I think I demonstrated this in the previous videos. We had something of this sort, -2. We are taking n as a natural number, so it's like we are having a finite subcover of this form, of that form. So you realize that if you look at this set is contained in here. Also, this set is contained in here. So you realize that this is the maximum element of this set. It's actually looking like an upper bound of that set. That's why we are trying now to construct that bound of A. Yes. So you have to let M be the maximum of these natural numbers. So if M is the maximum of those natural numbers, what next? If M is the maximum of those natural numbers, then if we try to get the union, remember A is now covered by those sets. So actually A is the union. No, A is contained. A is contained, is covered by the union from I equals 1 up to K, negative ni, and the union of this set here, the union is now equal to negative m. So this implies that A is contained in that interval. A is contained in that interval, implying that A is bounded. So we have been able to prove that every compact subset of R is closed and bounded. So that implies that as I demonstrated earlier, we have this interval here as closed and bounded. It's closed and bounded, so it's compact, and generally A, B is closed and bounded. Any interval of that form is closed and bounded, hence compact. So A and B are just real numbers. So thanks for watching.